Okay, today I'm going to do a one sample significance test for mean. So when I think of significance tests, I think of phantom. That's our little step-by-step thing that we're going to do. So P stands for parameter, H stands for hypotheses, A stands for assumptions or conditions that have to be met, N stands for name of the procedure, T stands for your test statistic, and O stands for obtain p-value, and M stands for make conclusion. Okay, so let's start. You can pause and read the problem and then come back. Alright, so for our P is our parameter. It's basically what we're trying to figure out, and what we're trying to figure out is the true mean DO level, I believe, dissolved oxygen level. So that's what we're trying to figure out, the true mean dissolved oxygen level. Okay, then what do we have? We have H, so our hypotheses. So our hypotheses, oh, real quick, sorry, forgot to add something. We have to say our mu. Okay. Mu is equal to the true mean DO level. Okay. And then our hypotheses, we have our null hypotheses, and we have our alternative hypotheses. So our null hypotheses is basically what is known to be true unless proven guilty, unless proven wrong or otherwise. So in this case, our mu, our parameter, we're going to say that it's equal, I think it's equal to 5, right? Because if it's 5, then our aquatic life is not at risk, because it says an average dissolved oxygen level below 5 milligrams per liter, I think it says, puts aquatic life at risk. So if it's at 5, it's not at risk. But we're trying to find if there's convincing evidence for the alternative hypotheses that that aquatic life is at risk. Aquatic life is at risk. And so what do they tell us? How do we know when aquatic life is at risk? Well, they say that an average dissolved oxygen level below 5 puts aquatic life at risk. So because of that, I already know that this is going to be less than 5. That's what we're trying to find convincing evidence for. Okay? So, here's the thing. Now we go to our assumptions. Well, actually, let me go a little bit back. So right now, they say that they took a random sample of 30 locations, and the mean, the average dissolved oxygen level was 4.77. And you might ask, well, 4.77 is less than 5, meaning that, aquatic life is at risk. But no. Here's the thing. Yeah, it is less than 5 in this sample, but just because it's less than 5 doesn't mean that it's actually less than 5 for the entire population, for like the entire stream. So it could have been that it could be less than 5 purely by chance. It could have just happened purely by chance. And it could be that the whole stream actually is greater than 5. So we're basically trying to find if this is significant enough, if this finding is significant enough. Like, do we have significant evidence? We do have evidence. This is our evidence. This is only some evidence. But we're trying to find if we have significant evidence. And how do we know that? By performing a significance test, a T significance test. Why not Z? Because we're not dealing with proportions, we're dealing with mean. That's why we call it a T significance test. And so hopefully that gives you a little bit of context of why we're doing this. This is evidence. It is less than 5, right? But we can't say that because it's only from one sample. I mean, you have a whole string as your population, right? And you're only taking one sample, and from there you're getting an average of 4.77 of dissolved oxygen. But what about all the other ones, All the other ones could be all greater than 5. They could be like 6. This could be like 7. And it could have just been purely by chance that this one was less than 5. So this is some evidence, yeah, but like it could be that these are all bigger, have a larger level of dissolved oxygen. So yeah, so that's that. Let me get rid of all of this. Okay, so our assumptions. So our assumptions are basically conditions that have to be met. So the first one is that the sample size has to be random. So it's usually a simple random sample, or it's given to you that it's random. So in this case, they do tell us that they have 30 randomly chosen locations. So our randomly, right here, we have, I'm going to say, condition is met, and then I'm going to provide a little evidence for it. So 30 randomly chosen locations. Okay, and then our second one is our 10% rule, I believe. Actually, hold on. What is that? No. Okay. Let me close this out. Whoops. Okay. Where were we? Okay, so our second assumption, or our second condition, is our 10% rule, which is that our sample size has to be less than or equal to 10% of the entire population. So what is our sample size? Our sample size was 30. It's 30 locations. Should be less than 10% of all locations in the stream, because that is your population. This is your population. So all locations in the stream, it should be less than 10%. Well, 30 should be less than 10% of all of the locations. If this condition is not met, then that means that your sample size would be too small. Actually, yeah, it would mean that your sample size would be too small to get an accurate p-value. Okay, so that condition is met. So we're going to say check that. Because even though we don't know the number of all locations in the stream, we can assume that the stream has a lot of locations, depending on what you would define a location. So we're going to say reasonably true. What happened? We're going to say condition met, reasonably true. Okay, so that condition is met. And then finally, we have the normality condition. Normality, or large counts. This is where your n, in this case, is greater than or equal to 30. This only happens when we're dealing with means. When it's proportions, it's something different. So you can check this in 3 ways. N is greater than or equal to 30. You can look at the graph of the data. If they give you data, you can plot it and look at the graph. Or 3, it's given to you that it's normal. But in this case, 30 is greater than or equal to 30. It's actually just equal to 30. So this condition is met, and we do not have to check the graph, and obviously it's not given to us. So yeah, so all our assumptions are met, so this means that we can now perform a significance test. Let's say if one of the assumptions, or more than one assumption, is not met, then we can say proceed with caution and then continue to perform a significance test. Okay. I'm going to put n over here. So n is the name of our procedure, and we have that up here. So it's a 1 sample. We can call it t-test for mu. That's what you would usually do in your test, and you can say mean if you want. And then our t is our test statistic, which is t. And this, in this case, it's actually our statistic minus our mu over our s standard deviation. I think it's like this. Alright, so yeah. Our s of x, which is standard deviation. Okay. So we have those numbers. So x bar, right, is 77. Mu is 5. You get this number over here. Whatever these two numbers are is the number that you put in here. Okay. And you divide by standard deviation, which was given to us somewhere over here. Standard deviation is 0.939. 0.939 divided by the square roots of 30. Okay, you could do the math in your calculator. Let me just do the math. Hold up, let me get my calculator. So this should give you negative 0.23 over 0.17143761605, and then negative 0.23 divided by that answer is negative 1.342. We round, so little side note, we round our test statistic by 3 decimal places. Okay, so it's a little side note. So this is your test statistic. Great. Now you might wonder, why do we need that? Well, we need that to obtain the p-value. So here's the thing. If you have a TI-83, I don't think you can do this, but if you have a TI-84, you can. But I'm going to show you how to do this with the TI-83. Well, the thing is that you can't do it with the TI-83. You're going to have to borrow a TI-84. But if you're at home and you're trying to do your homework, I wrote a little function that you could use. So this helps you, well, this is a test statistic, but this helps you get your p-value. So this is going to be linked down in the description box below. It's under hypotheses test, one sample, t significance test from you. And all you have to do, right, is go here, okay, go at the last line, and just input the variables that are up here. So you put n is 30, your mu is 5, and then you put your test statistic in here, okay? If you don't have your test statistic, then you can find it using the function that I have right above it. So all you have to do is put in your n, which is 30, your standard deviation, which is 0.939, your x bar, which is 4.77, and your mu, which is 5. And then we'll give you your t-statistic, and then you can just plug it in right there, okay? And then it'll tell you what your p-value is, 0.9. So that would be your p-value. But if you're looking to do it by hand, hold on, give me 1 second. Where's my whiteboard? If you're looking to do it by hand, then what you're trying to find is that your p, hold on. You're trying to find the probability. Hold up. I think you do it with TCDF. What happened? Actually, if you were to draw a picture, you would find where this is. Oh my god, what is happening? And I think what we're trying to find is less than this. So basically the probability that t is a t. Let's see, hold on. trying to find the probability that that mu is less than that. Okay, 1 second. So where are we? Okay. My bad. This is actually supposed to be, right, 4.77, and this is supposed to be 5. Okay, so what we're trying to find, right, is the probability, you know, that that mu is going to be less than, well, actually, this is our average. But anything less than 5, right? Anything less than 5 is going to be a risk for aquatic life. So that's what we're trying to do. So really, we're doing a one-tailed test. So to obtain a p-value, you want to use TCDF in your in your calculator, excuse me. And then do 1E99, and do up to -1.342, because that's your t-test. And then when you're dealing with t, you have to use a degree of freedom. So your degree of freedom is going to be 29, because degree of freedom is your n minus 1. So you know that n is 30. So 30 minus 1 is 29. So essentially it's going to be TCDF, and it's going to be, what is it again? Oh, so it's going to be your lower bound, your upper bound, and then your degree of freedom. And your upper bound is your T stat. That's how you get your p-value. You plug that into the calculator, and it's going to give you something like, it's going to give you 0.9. I have the answer key for this, so hold up. Yeah, so it's going to give you 0.097. And my answer gave you 0.9? What? Oh, because I forgot to, whoops. Degree of freedom is n minus 130, okay. No. What if I use their p-value? Negative, well, 1.33? I didn't round anything, so... .903. They said 0.097. That's interesting, because in my calculator, I do have that, so... I don't think this is accurate then. So I'm thinking that maybe all I had to do was do 1 minus that answer. If it's, okay, hold on. If my test statistic was this, and I can run that, it's a no. And then do another code and just do 1 minus that. Oh, there we go. See? That's what's wrong. Because, okay, I can't believe I erased all my work just because I thought that I was wrong. I was not. Okay, so it turns out for the obtaining p-value, okay, so I'm going to show you something. What even am I doing? Okay. So, I'm going to show you the difference between a 1 tail, 2 tails, and, well, this is right-tailed, left-tailed. So left-tailed is when you have, well, let me show you the difference here. Is when you have a certain, this is your mean, right? And then you have a certain value. Let's say your value is something over here, something over here. It's the same thing. When your HA is when, let's say your mu is less than a certain value, then that certain value, well, it's basically this, and then this means that it's, oh, wait, no, this is this, this is this, this is when it's greater than a certain value, and then this is when we don't want any of it. we want the probability of not having any of this. Okay, this is when it's not equal to that certain value. This is when it is less than that certain value. So we're trying to find this one, and because, well, you're not going to get it, because this is, well, whatever. I had to take the p-value and do 1 minus because it was less than. Because it calculates p-value only for greater than. And I did account for this condition of 2 tails, but I didn't account for this condition, like if it's going to be less than. So when it's less than, I have to do 1 minus the pink. So 1 is basically the whole thing, and then the pink, which is the probability value, this is what it calculates. Well, it's actually calculating, let me tell you, it's actually calculating this when I'm asking for this. So when I do 1 minus that p-value, it's going to give me this. And that's what I want, which is this, right? Hopefully that makes sense. I'm going to restart the video and do this again because, yeah. Okay, let me delete all of this. Why is it not erasing? Why aren't you erasing? Why aren't you erasing? Oh my god. Okay. Okay, so then elif type test is equal to right, then your p-value is just equal to the area. Why is it like this? Is your test left, right, two-tailed? My test is left-tailed. There we go. Oh my god, I'm so proud of myself. Thank you, God. Okay. Nice. And let me try these. So if I do this one, well, that one's fine. But what if it's a right? If it's a right one. Let me do right-tailed test example for T. Okay, let me try this example. So a high-end computer manufacturer, blah, blah, blah. The company random selects 40. So let me just make sure that this is right in all locations. So we have 40. Our value is 1,800. What's the other one? Our test statistic. What is it? No! Why is it a Z? I need it to be a T. It's a right-tailed. I need it to be but this was Z. I need it to be T. Okay, good. So here they give me the stuff. So let's do 5. What did they say? 590. Oh, actually, no. What's the mu? Oh, they don't want the sample size. Jesus. They want the... Actually, they do. What am I saying? Oh, because I already have the test statistic. This is a test statistic. That's what I need. Okay, so plug that in there. It is... What's the sample size again? Sample size is 5. And then 90 is our number here. Okay, run that. This is a right tail test. Ugh. Right. Right. Oh my god. Right. Thank you. So what's our thing? What's our p-value? Is greater than 2.130. Oh my god. But we don't need that. That's for confidence interval. Confidence level. Oh. Okay, so let me do 36. $23. And then the test statistic. Why? Yo, why is it a Z? It's not supposed to be Z. What is it? 2 point...
Is the test statistic.
Okay, it's 2.225. Run that, and it should give us the answer that they have here.
Scale over
0.0122. It is a right. 0.0154. Okay, that's fine. It's just 2 decimal places off. Oh my god. I don't know. I just don't like that it's off by like 1 decimal place. Mm. Okay, so we don't want anything less than that, so this is a left-tailed. Okay. Did I get it? 2.078. Negative 2.078. Yeah, I got it. Okay, that's a good test statistic. And then what? What's the p-value? Wait. So we're calculating the probability that z is less than negative 2.0784. But where's the p-value though? No one's telling me where the p-value is. Well, it is definitely less than 0.05. Meaning we reject the null hypotheses. Meaning that it is, that those levels... What was he even testing? I forgot what I read. Something about... I don't even know. This was a great video. Even though I didn't hear a word of it, but I got the idea. Well, this one is definitely right. I should go back to this video. Wait. Okay, it should give us 2.25. Yeah, okay, perfect. So then this is good. See, that's what I'm saying. Like, this function is a little bit off. Like, it gives me the area, but it's like a little bit off. But it's giving me like at least, the first 2 decimal points. I think it's fine. I just wanted to like double check. This one's definitely fine as well. But then I don't know if the p-value is right because the other guy didn't do the p-value. So how am I supposed to know? You know what? Let me just go back and do... right-tailed test for mean. Okay, so 3.56. Okay. So let me look at the information and also try it again. I'm just gonna put it all in one because I'm so tired of doing like two. Okay, so to find the test statistic, let's look at the data. So what is N? The sample size is 100 students, so it's 100. The standard deviation is 43.20. 43.20. The mean cost is $315. 15.40. And it is known to be $300. And so that means whatever we get here is this. So I'm gonna put that in there. It's known to be 300 and the sample size is 100. So let's run that. And it is I think, what did it say? Above? Is there evidence that the population mean is above 300? 0.0. Okay, so it should be 3.56, right? We got 3.56, perfect. And let's look at what they got for the p-value. I hate when they use a z-table. It's my worst nightmare. What's the p-value? Are you kidding? I don't have time for ads. I'm craving McDonald's fries right now. Oh my god, I want McDonald's fries so bad. Yo, can someone tell me, why do they never say the p-value? Like, hello? What? They didn't find the p-value. Oh my god. What is the p-value? Is it 1.29? No. Oh yeah, it is 1.29. But is that the t-table? Why? It means they're looking for greater than 300. So that means it's a right tail test. So the probability, the p-value is 1.291. But over here, 0.028. Interesting.
We know is that our critical value is somewhere between these.
Oh my god. Oh, is that why? Okay, well. This is so annoying. I'm not even sure what I'm doing anymore. It is less than 0.05. It's definitely less than 0.05. So that means we reject all and have convincing evidence for HA. Oh, this is horrible. What if I just search it up? The director of admissions. At a large university. Advises parents of incoming students about the cost. About the cost of textbooks. No, yes. Okay. T is greater than 1 point. What? Wait, honey, can you just back up for a second? I should probably go to sleep. Like, I really should. Tomorrow's Sunday, so I should have been sleeping at 9:10, the minimum. Okay, blah, 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 blah. What? 1.9842? Am I going crazy? But, like, it's not supposed... What is this number? It's just supposed to be your p-value. Is that your p-value? 0.01 significance level. 100, right? And then it's supposed to... It's known for 300. Because that's what mu is. And then your test statistic. I don't know.